I'm Megan DeMello.
And I'm John Erickson, and we're going to talk about our heat exchanger optimization.
The problem was to create a heat exchanger that will transfer 1 megawatt of thermal energy. In the problem overview, there were variables that had given values and variables in which the teams had to create their own values. During the modeling approach, we decided on 50% propylene glycol as our working fluid. This is because it prevents against corrosion, has a low toxicity, and the burst and freezing. It protects against burst and freezing for the pipes. The material that we chose was aluminum 661T6. That's because it has a high thermal conductivity, it works well with potable water, and T6 alloys has a higher toughness and strength than copper.
Using HEEDS, we optimize our heat exchanger. We use 4 variables. We use the tube length, the number of baffles, the velocity of the fluid, and the velocity of the river water to be our design variables. We also had a numerous amount of responses associated with those. And those responses are kind of what we had to use for our objective and what we want to maximize, minimize, and also our constraint as well. We decided we wanted to minimize our pressure drop, delta P1 and delta P2, and we also wanted to maximize our efficiency, the NTU. But since the efficiency is so small, we'd use a weight factor of 100 in order to get it bigger so HEEDS has a better chance of reaching a better solution. We also made one constraint that the baffle spacing needed to be at least 1/5 of the total length found. The optimal solution in HEEDS was found, and the results are shown here in the slide. It's actually 206 tubes. They are 1/4 inch tubes, schedule 40. It uses 1 baffle. It's 20 feet in length, has a beta of 149.615, and an efficiency of about 0.34. Along with this design, there are a few recommendations we make. One is to keep the velocity between about 1.4 and 2.0. This is mostly because of corrosion and erosion. High velocity will increase the amount of erosion, and a low velocity could lead to stagnation and create corrosion as well. And we also do recommend that we utilize some kind of filter or screen in order to eliminate dirt, sand, or any other abrasive material from entering the heat exchanger. And this is going to help with the longevity and help reduce maintenance as well.
In conclusion, we decided chemical cleaning was the best way to go due to the number of pipes that we have and because we chose a triangle orientation. We also decided that chlorine would help in a microbiome buildup. And finally, we decided on Exeter Company for our supplier due to the fact that they specialize in high performance heat exchangers. They also perform well in high temperatures, high pressure, and highly corrosive environments, and they pride themselves on safety and sanitation. Any questions?